In this video we're going to look at an optimization problem. The postal office will accept packages only if the length plus the girth is no more than 240 inches. See the figure, and it's a little small here. I'll redraw it. So the girth is the length around the base, so this plus this plus this plus this, and then we get the length here. Now, assuming that the front face of the package is square, what is the largest volume package that the Postal Service will accept? So it's square, so we know that this side's x plus x, this side's x, and this side's x, and then we got our length L. So the girth plus the length can be no more than 240 inches. So we have x plus x plus x plus x. So our constraint is that 4x plus L has to equal 240. Now what is it we want to do? We want to maximize volume. So we need the volume of this thing. Well, the volume is the area of the base times the height. So volume is going to be x times x, so x squared times L. And here's what we want to maximize this subject to that constraint. So what we want to do is we want to get that volume in terms of one variable. So let's solve this for L. So L equals 240 minus x, minus 4x, and we're going to plug that into this L to get our volume in terms of just one variable, x squared times 240 minus 4x equals 240x squared minus 4x cubed. So there's our volume function. What we're going to do is take its derivative and set it to 0. So take the derivative, we have 480x, just have a couple of power rules, minus 12x squared. Like I said, we'll set that to 0, and we can factor out a 12x, and if we factor out a 12x, we get times 40 minus x equals 0. So we get two values for x. We're going to get 0, which would leave us with no box, and we're going to get 40. So the value we're interested in is x equals 40. Now we do want to check and make sure this is a maximum, so we're going to use the second derivative for that. Second derivative is 480 minus 24x, and what you do is you plug in the 40. Well, 20 would make this 0, so this is going to make 40 is going to make this negative. The reason we care about that means at 40 this thing is concave down, which makes our value a maximum. So when x equals 40, this thing is going to be at a maximum. Now we wanted to find the maximum volume, so we know that x has to be 40. L, well, let's just go back to here, plug in 40. So 240 minus 4 times 40, which is 160, is 80. So there's our L. And so the volume that would maximize this thing, or our maximum volume is 40 squared times 80. So 40 squared times 80, which is 128,000, and our units were inches, so this is going to be cubic inches. And so that's how we can maximize.